So good morning, everybody. So it's a great pleasure to be here today to talk about the ALMA large program COMPASS. So COMPASS stands for Complex Organic Molecules in Protostar with ALMA Spectral Surveys. So it's a project that we started 2 years ago. But before I tell you more about this program, let me give you a bit more of context. So the hot core nodes are the warm inner regions of solar-type protostars that are particularly rich in complex organic molecules. And the high abundances of complex organic molecules in the inner region can be explained by the thermal absorption of the molecules frozen on grains when the temperature is sufficiently high, so typically above 100 K. So the size of these hot cores are about tens, hundreds of astronomical units, depending on the luminosity. And so if we observe them with interferometers such as ALMA and NOEMA, we can have a good knowledge of their chemical content. So these hot cores can be found at the earliest stages of the star formation process, so most of them at the class 0 stage, and also for some of them at the class 1 stage. So as you know, the chemistry, the organic chemistry is also very rich on comets and asteroids, with, for example, the presence of amino acids and sugars. So the question is then to know if there is an inheritance of the chemical composition from the earliest stages of the star formation process during the formation of planets, comets, and asteroids. So to answer this question, we need to know the chemical content of these hot cores. And for that, we can use large spectral surveys. So large spectral surveys have different advantages. So first, they allow us to characterize the chemical composition in an unbiased way, and so to know the degree of complexity of the sources. We can also have some unexpected detection of molecules, and it also leads to better models due to a higher number of detected transitions. And in this case, we get better constraint on Coulomb densities and excitation temperatures. And knowing the abundances of the maximum of species is really important for the chemical modeling of the sources. So it allows us to better constrain the formation pathways and reaction rates. And so with a large spectral survey with ALMA and NOEMA, we can characterize the chemical content of these hot cores. So we started 10 years ago with the ALMA PIL survey, which is a large spectral survey with ALMA of the protostar IRAP, which is located in the Ophiuchus cloud. And this large spectral survey covers a range between 329 and 363 gigahertz. And it is more sensitive by a factor 10 than all the previous survey of these sources. So thanks to that, we managed to detect a lot of molecules in this source, with also some first detection in solar-type protostars and in the interstellar medium. So here you have a summary of all the molecules that we detected here. So the goal is not to read the molecules here, but to see that their abundances with respect to methanol can be up to 6 orders of magnitude lower. And here you can see comparison between the chemical content of IRAP and the chemical content of the comet 67P. So we see an interesting correlation within approximately 1 order of magnitude for the O-bearing molecules and also for nitrogen-bearing molecules. So the question is then to know if the chemical composition of IRAP is similar to other low-mass protostars. And we also want to know what are the physical, environmental, and evolutionary regulators of the formation of the complex organic molecules. So is there a universal outcome of the chemistry of the complex organic molecules? And how much diversity in organics can we expect for planetary systems? So to answer this question, we started the large program COMPASS. So it's a cycle-land large program. So it represents 125 hours of observing time with a 12-meter array. And the goal is to carry out large spectral survey of 11 low-mass protostars at a relatively close distance, so less than 500 parsec. So we check before submitting the proposal that all these sources contain complex organic molecules in their inner region. And regarding the characteristic of a survey, The spectral coverage is not exactly the same as pulse. It's at a slightly lower frequency. It's also in band 7, but between 279 and 312 gigahertz. And the reason for which we choose a different range is that it's more difficult to observe at higher frequency. And when you want to observe so many sources, we need to optimize that. So the angular resolution is between 0.3 and 0.5 arcseconds, except for two close binaries, because we wanted to distinguish the two binaries. So we ask for these sources 0.1, 0.2 arcseconds. And the spectral resolution is sufficient to resolve line profile. So I am one of the copy of this large program, which is also led by Jess Jørgensen, Maria Drozowskaja, Jungen Lee, and Adele Plunkett. We have also a lot of co-Is and a lot of PhD students and postdocs join this project since the beginning. So here you can see the compass sources and that they come from diverse environments. So here you can see the column density map obtained with Herschel. So we have sources in Serpens Main, Serpens South. You can see here that is a very dense region in Perseus and also in Orion. So here you see, for example, the very nice filament in our Orion A. And we also have sources that come from more isolated environments. So L1551 IS5, BHR71, and B335. So IRAP 1629 is not part of COMPASS, but of course, we will compare the result with PILS. So here you can see the SCD of these sources. So it allows us to estimate the bolometric luminosity. So in red, you have more luminous sources, and in light color, you have the less luminous sources. And we also estimated the bolometric temperatures, which should be related to the evolutionary stages of these sources. So in red, you have the youngest sources, and in blue, the most evolved sources. So the COMPASS observation started early 2022, and the last observation were obtained at the end of August, of last August. And for several of the sources, we only obtained the observation this summer. However, there is one source that was fully observed very early. It's BHR71IS1. And you can see here the full survey of this source. So there are a lot of lines. So we estimated there are about 4,000 lines. And of course, we have to identify all these lines. Here you can see a part of a spectral survey that was also observed for other sources relatively early. So we compared this spectral band between the 5 sources. So it can look relatively similar, but when you zoom in here, you can already see some differences. So for example, here we have some methylformate transition that are bright in some sources, faint in others, and not detected in some sources. Another example is CD3OH, where you can see some emission for 4 sources, but not in V883ORI. So we do not know yet if it's due to different physical excitation or to difference in the chemistry. So it's what we want to answer. So now I'm going to present you the first result that we obtained with COMPASS. So most of them are on BHR71. And in particularly, I led a study about the deuteration of methanol. So we detected, so of course, the main isotopologue methanol, but also the 13C and the 18 oxygen isotopologues. And regarding the deuterated species, we have CH2DOH, CHD2OH, CD3OH, and CH3OD. For CD3OD, we can derive an upper limit. And so for this molecule, I derived column density, and I could only do it for most of the deuterated species, thanks to recent spectroscopic work. So here you can see some line of CD3OH, for example. So you can see that they are relatively bright. And here you have the maps of the different isotopologues. The emission is compact, so the emission comes from the warm inner regions. So I analyzed the spectra at the continuum peak position, and I found that the excitation temperature is about 140 K. And the column density of methanol is about 210 to 19 per square centimeter based on the 18 oxygen and 13C isotopologues. So here you have the D2H ratio. So these are not column density ratio, but so here they are statistically corrected. So here you have the D2H ratio for the hydroxyl group and here for the methyl group. So what we see is that the deterioration is higher on the methyl group than on the hydroxyl group. So we have 2% for CH2DOH and 1% for CH3OD. So it is something that was already found earlier in other studies, both with single-use telescopes and interferometers. So it's also seen for IRAP 1629.3. And what we see also is that the deterioration increases with the number of D atoms on the methyl group. So for example, for CH-D2OH, you have 11%, CD3OH, you have 24%. And the upper limit for CD3OD is consistent with CD3OH. Another study led by Pune Nazari is about the isotopic fractionation of methyl cyanide. So she found that the column density for the two 13C isotopologues are similar. So it is something that was also found for IRAP 1623 and Sagittarius B2. So Sagittarius B2 is a IMA star-forming region close to the galactic center. But there is a different degree of deterioration. So for example, here you have CH D2CN over CH2DCN. And you can see that it's higher for BHR71 than IRAP 1629.3. But for the CH2DCN, CH3CN ratio, it's relatively similar. And for the 15N fractionation, it's relatively consistent with IRAP 1629.3 and maybe slightly higher than Sagittarius B2. There is also a study about the spatial variation of molecules at large scales led by Young-Sik Yoon. So this is a study using PCI method. So PCI means principal component analysis. So it's a way to recover the lines showing extended emission by breaking it down into principal components. So it was previously used for a study of B88 so here it was applied for BHR71. And it's important to recover the extended emission from faint lines and also describe the physical origin of different species. So here you can see some methanol emission, so methanol with low excitation. So you can see that can be extended in some outflows. And last study is about methanol maser emission, but this time in some of the Orion sources. So we didn't have all the spectral coverage, but we detected methanol class 1 maser emission at 302 gigahertz. So it is detected around OPS 108 and OPS 373. So here you have in green the continuum emission of these sources. And in red, you have this emission, this maser emission. So for example, in OPS 108, you have the emission here. And it's a very bright emission because it's more than 1000 K. So it's really maser emission. In OPS 373, there is a maser emission here. So it's not as bright, but it's not thermal emission. And in V883, we do not detect maser emission, it's just thermal emission. So these methanol class 1 masers are in fact pumped by collision and they are associated with outflow shocks in star-forming regions. And so for this source, we know that this maser emission is induced by an outflow driven by a source that is not visible in this map, that is located somewhere here, that is OPS 370. And for this maser emission, it is due to the outflow of OPS 373. And we also found an interesting correlation with acetaldehyde, since there is an arrangement of acetaldehyde where there are methanol masing components. So to finish, here just a quick summary of this presentation. So our goal is to know if there is a chemical diversity between solar type protostars, and we can answer this question with large spectral survey and with the large program COMPASS. So we are really looking forward to analyze the data of all these protostars and to compare that with IRAP 162093. So as I show, the first results are now coming, but more should be expected with a cross comparison of all sources. So thank you for the attention.